All right, so welcome everybody for this week Conjecture seminar. Thanks for being here. It's my pleasure to introduce Vincenzo Mantova from University of Leeds, and he will speak about intersecting the graph of X with complex algebraic varieties.
Right, thank you. Thank you very much for the invitation. Thanks to everybody for coming. I actually have never been to this seminar, of course, distance and everything. Okay, so as I talk about, I hope you find this, all of this stuff interesting. So the problem is what it says in the title. You take the graph of the complex exponential function, which is a transcendental function. You want to know whether it touches algebraic varieties or not. Okay, let me make this a bit more precise. I'll give you a bit of context. Okay, so let me fix some notation first. Just let me get this out of the way. So I'm going to use gamma for the graph of the exponential function in C times C star. Okay, nothing strange. So this is just exp. And then I'm going to take, I called V, an algebraic variety in C times C star to the n. Okay, so we take powers. And okay, now this is the bit of notation that we have to keep in mind along the way, because I'm going to use it a few times. So I'm going to call pi a, the projection from the variety V to the C to the n. That would be the domain part of this graph. And pi m is the projection onto C star, onto the codomain. So A stands for additive, because this is the additive group, C to the n, and for the multiplicative group, C star to the n. Okay, so hopefully this will be all clear. So this is just notation. Okay, so the question is whether if you take an algebraic variety like this, is it going to intersect the nth power of the graph of exp? Okay, let me give you a very concrete example. When n is equal to 1, then an algebraic variety says just defined by one polynomial in two variables, so p z w equal to 0. And then this intersection means that I'm looking for the points z e to z such that p of z e to z is equal to 0. Okay, so as I'm going to, so especially when n is equal to 1, I'm literally trying to solve polynomial exponential equations like this, where you plug one exp inside your polynomial. And then in general, when n is bigger, that just means we're looking at systems of polynomials exponential equations rather than just one equation. Okay, so are we supposed to find these intersections or not? Well, the idea would be, exp is a transcendental function, so not too many. Now, actually giving a restriction is obstructions is not great. So let me say this just for a moment. Okay, so let's entertain this idea. So assume Chandler's conjecture and Zilberpink for the multiplicative group. It's just to understand what's going on. What kind of challenges there are if you really want to do something precise. Okay, and now if you take an algebraic variety defined over Q of dimension less than n, and then there's an extra condition, the projection onto the multiplicative side of V, so onto the codomain is not contained in any proper algebraic coset, then this intersection is not a risky dense in V. Okay, I can't quite say it's not empty. There might still be points around, but it's very constrained. And the point is, Chandler's conjecture says exactly this statement here. It takes z e to z1, z1 e to z1, zn e to zn, point in an algebraic variety. If this happens, then this point has this tuple has transcendence degree less than n over q. And then Chandler's conjecture says, okay, in this case, the points z1, zn are linearly independent over q. So there are some rational numbers or some integers, if you want, not all 0, such that this is equal to 0. That means that this point lies in a linear subspace of c to the n, proper one. And then I can just play now with whatever I have in front of me. I can take the minimal subspace with this property. And then I can check that if I take exp of this, I do a bit of shuffling of things, but I find an unlikely intersection. So if you know about Zilberpink, that That's an unlikely intersection, and that means if zebra-ping is true, then this is contained in it's going to contain in one of finitely many algebraic subgroups. So you can say, okay, the intersections are coming from these sub-varieties of V, not from V itself. So there's a, so you can go down. Okay, so this is a complicated way of saying that if the dimension of V is less than n, then it becomes really tricky. Okay, but then the general idea is that anyway, the graph of x to the n is an analytic set of dimension n. The ambient space C cross C star to the n has dimension 2n. So you expect to find intersections when the dimension of V is at least n as well. Okay, so you can keep this in mind. And when you go lower, then it's arithmetic gets in the way and it gets complicated. Okay, and actually I should mention that there is something better that we know. We know that there is a true form of Chalmers modular countable subfield of the complex numbers, so a countable field F. Of course, we have no idea what this F is. If Chalmers conjecture is true, then you can take Q, but it's going to be essentially the algebraic closure of Q, and it's going to be understandable, but otherwise, there's we don't know. Okay, now in this situation, you can do, for example, you can say that if V is defined over the subfield, dimension less than n, again, you need this condition about projection of V not being in a proper coset, then this set is at most countable. Okay, so you still don't quite get this, you don't get that this set is empty, but you can understand something about it. Okay, so this is just to say, let's say that the dimension of V is at least n, because otherwise it's a bit of a nightmare, and it's not the kind of reasoning that I'm interested about right now. So let's go the other way, and let's look for geometric conditions on the algebraic variety V that then shows that this intersection is non-empty between V and gamma to the n. Okay, and it's better. Okay, it's better in a way that in the sense that there's a theorem. I mean, first there's a conjecture, okay, by Zilber that says that when the variety satisfies two conditions that I'm going to define in a moment, so if the algebraic variety is 3 and x normal, whatever that means, then this intersection is non-empty. So you can find points of the graph of x on the algebraic variety. Okay, what are these conditions? The first one is similar to what was in the previous slide, is freeness. So a variety is free when, and now you do two projections. You project onto the additive side, onto C to the n, and you want this to be not contained in any translate of a proper Q-linear subspace of C to the n. Okay, so we just seen on the previous slide, I was saying, but Chalmers conjecture tells you something about but when the points are low transcendence degree, then they lie on some Q-linear subspace of C to the n. So this is a similar situation. And you want to have the same for the projection onto the multiplicative side. And now, of course, instead of having a translate of a Q-linear space, you're going to have an algebraic subgroup, which is going to be of the form exponential for some n like this. And then x normal.
Is there misprint?
Hmm?
Is there misprint in your phi and the other phi?
Oh, sorry. Okay. The type, of course. Yes, I didn't fix all of them. I apologize. Let's see if I can. I mean, I can do this now, but it's not going to. It's going to disappear very soon. Yes, it's supposed to be phi, not phi, not var phi. Thank you. Okay, so x normal means that this is a bit tricky to explain. I mean, this is the shortest way I know of describing this condition with this endomorphism, but the idea is, first of all, this is saying that the dimension of V is at least n. But then it also says, I mean, if I do, this stuff, this C cross C star is a group, it's an algebraic group. So there's an additive group here on C, multiplicative group on C star. And if I take the endomorphism of the group that preserve the graph of the exponential function, in a weak sense, it just means that the image of gamma to the n is a subset of gamma to the n. Then in this case, if you apply phi, if there is an intersection between v and gamma to the n, then you're going to find an intersection between phi of v and the image of gamma to the n. Okay, if you apply any endomorphism, which means that, I mean, you want to be careful about those as well. I mean, if the dimension of v drops when you do this too much, then you don't expect to find intersections after you apply phi. So there shouldn't have been intersections in the first place. Okay, so saying dimension of v greater than at least 10 is not quite enough. You also need to take into account the group structure of this variety here. Okay, now it doesn't matter for this talk, now the details of this, but I hope it gives you a flavor of what's going on, because we're going to do special cases where these conditions are for free. You have them already by construction. And that's probably also why we can actually prove something, because this accounting for this is not always trivial. Okay, now the theorem is that if this conjecture is true, so if every variety which is free and normal intersects the graph of the exponential function, then there's something that we model theorists like very much. So the structure complex exponentiation is quasi-minimal. Every definable set is either countable or co-countable here in C. And there's also an uncountably categorical axiomatization in a suitable infinitary language. Now, if you don't care about all this quasi-minimality, you should, I think, but there's people of different interests. The point of this categoricity is that once you know that exponential algebraic closure is true, then you know that whether V intersects gamma to the n is determined by the geometry of V and this subfield F over which Chandler's conjecture is true. So these two pieces of information, they determine everything else. So there's nothing, so there's a bit of arithmetic coming from here, and then the rest is all geometry. And by geometry, I means these kind of considerations about the dimensions of the variety after endomorphisms and stuff like that. Okay, so that's sort of the explanation that I will give, the meaning. Once you know this, then you can figure out everything. Even though, as I said, I mean, it becomes tricky to, if you want to say this explicitly, when does V intersect gamma to the n, then become messy. But the point is, it's determined once you know if this is true. Okay, is it true? We know a few cases. Okay, one case which is easy, and that's the first one. I mean, the one I'm going to talk about first, because it leads to the main stuff, is this one. If you work in n equals 1, and you have an algebraic variety which projects dominantly onto both C and C star, dominant means, I mean, the projection is essentially surjective of dimension 1 in this case. That's an easy calculation. So we're going to do this quickly. There's and then you can ask David in the audience. I saw him there. Okay. So, and this you can do with classical complex analysis. And now just a reminder, you should think this case is essentially, oh, let me make my pen thicker. This is essentially solving equations like P of Z e to Z equals 0. Essentially. Okay. And we know how to do those. Okay, then there's another case, which I'm not going to explain, but I'm going to mention it. It's actually comes from, it's pretty old in a sense compared to the age of the entire, compared to the conjecture itself. When V splits as a product of two subvarieties where one is linear living in the domain, so in the domain part of the graph in the C to the n, and then W is in C star to the n, and there are conditions which I will refrain from describing on this. L should be generic enough, so think of a random linear subspace of C to the n. Then you can find intersections between this algebraic variety and the graph of X. Okay, and now the method is different. Zilber was using stuff about these Kowansky's phenomenons, because the point is that the linear subspace of C to the n, when you take the exponentials, you're going to see something that looks like the function raising to powers. Okay, so if this linear subspace is y equals lambda x, then you're going to have e2x and e2 lambda x that are points that you want to be on this algebraic variety W. Okay. Now, sorry if I'm going through this a bit quickly, but there's also the case, this is a big case in the sense it's a big family of algebraic varieties. Suppose that V is an algebraic variety whose projection to the domain, C to the n, is dominant, so it has dimension n. Then in this case, V intersects the graph of X, intersects gamma to the n for every n. And it doesn't even matter whether V is free, X normal. I mean, nothing matters. First of all, because if this projection is of dimension n, it turns out that X normal is always X normal, and it doesn't need to be free. Now, this was a bit of a surprise, I think, for us at least, people studying this conjecture. But then when you see the proof, it makes sense. Okay. And now the final case, which is the one I want to talk about today, is this one here. You take V of dimension at least n, so you want to have this condition. I'm not going to say X normal. This is another case where it actually comes out for free. And when the projection of V to Cn is of dimension 1. Okay, so for the people in the audience who have read these papers about V projection V to C to the n, this is the dual case in a sense. I mean, this is when the projection has maximum possible dimension, and this is where the projection has minimum possible dimension. Okay, and the technique is completely different. And yes, and then I forgot to say, of course, something. There's also a condition about freeness, but it's going to come up in a moment. So I'm going to fix this small typo here. Okay, so this is the situation. We know how to intersect some varieties with the graph of X. And now let's talk about how we do this one. So you can do this with fairly elementary tools, after all. Okay, so let's start from something even more basic. So let's go back to this kind of equation here. So we work in the case n equals 1. And in particular, it means that this was meant to be crossed. So take V variety defined by Z equal W and C cross C star. So let me just point out now, I'm going to use this convention that the variables Z are the additive ones and W are the multiplicative ones corresponding to C star. Okay, so if I take this variety, then the intersection of V with the graph of X, it just means that we're looking for the points such that Z is equal to E to Z, this kind of equation. Okay, do you think this set is empty, finite, infinite?
No. 1 point, 2 points.
I think 2 points, or
2 points, yeah.
it's the Lambert W function comes to mind.
Mm-hmm.
Yeah. Okay, yeah, so if you look at the real part of this graph, then it's going to be 2 points. 2 points?
Yeah.
Yeah, but if you look at the complex numbers, it's actually going to be infinite. Okay, and there's the intuitive explanation, I would say that there's I think it's just better if I just show you what goes on, rather than me saying something vague and probably misleading.
I think Collis has a paper on this.
Hmm?
Collis has a paper on this. I think it's called, I mean, it has a name. I forgot what it was. It started with a W something. Never mind.
Yeah. I mean, I should say that, you know, this particular case is really old style complex analysis, and I mean, so for example, from my experience, I know that David wrote a paper in the 90s talking about this, but his main work was about the actual properties of the points on the graph. But I think that the fact that there are solutions, that there are infinitely many points, that's the, let's say, Hadamard factorization problem, if you want.
I'd like to change my answer to infinitely many. I should have just said. I mean, yes, real expected to just from the Lambert W function.
Yeah.
I don't mean to bring up my own work with the trinomial, but that's even the case of where it's a trinomial equation, z plus z to an alpha, where alpha is a complex, equals a constant, has infinitely many solutions. In fact, that's what I've been trying to compute on in Python. But I mean, I have the math formula. I mean, infinite series, and there's a parameter in there generates infinitely many roots, but computing it has just been devilishly difficult. I think I can only get like 2 or not even 3, but like 2 roots computationally, because all the others either like are insanely close to 0 or close to infinity, and they're too hard to compute on Python. I mean, I just had to. But yeah, so if you actually try to stick that into a computer and try to get all those infinitely many roots, it's
yes. No, I mean, no, you're raising an interesting point. So maybe we'll talk about this later. Like the computing this stuff is, it's not easy. It's not always easy. So in this case, you know that in this case, the essential singularity is at infinity. And so you expect to find solutions going further and further away. And I think in this case, there's explicit descriptions of this, the distribution of these points. So they can't grow too fast as you move away. So the next 0 is not too far away, but it's also not too close. But I prefer not to say too much because I don't actually know much about it. So I'm coming from a very different angle. But yes, so we also did try to do some explicit calculation, but not me, David tried to do this. But yeah, it looks challenging for the computer. Okay, so let's see what happens here. So this, as I said, this is actually easy to explain. So suppose there could be a contradiction that this function is not 0, it's never 0. Okay, so it doesn't vanish anywhere. Well, then there's an easy thing you can say. Well, if a function never vanishes on C, then it's exp of some other function, some other holomorphic function phi from C to C. Okay, so I just take the log basically, and I can do this because the function is never 0. And then I look at this function. Now, this is a holomorphic function from C to C. I look at what happens when you go to infinity. And now, of course, this is there are some calculations, but it's not, a half page. And you can see that this phi has to be just a linear function. Actually, even with coefficient 1, it has to be z plus c. Okay, because the growth of this e to z is dominating everything for f, and so if f is equal to e to phi, then phi itself has to be essentially e to z. Okay, now in this case, we're done already, because now we have e to z, this f of z is e to z minus z equals to e to z times a constant, which is an algebraic relation of e to z over z. Okay, but we know that e to z is a transcendental function. So this cannot happen at all. We can't have this equality here, this algebraic relation. Contradiction, so there must be 0. Okay, so I said it would be easy. I mean, unless I said something very, very wrong on the second line. I mean, but this is the essence of this proof. Well, this kind of argument at least. Okay, now to show that this set is infinite. Okay. Well, you just say, well, suppose that there are finite many zeros, z0, z naught, zn, with they're going to have multiplicities m naught and n. And well, you just change the conversation a bit. You take, instead of looking at f of z, this function here, you just divide e to z minus z by these monomials, these binomials, z minus z naught to an appropriate power, so minus the multiplicity. And of course, now this is a function that does not vanish on the complex numbers. Okay, and there are no poles. Okay, so I'm not introducing some singularities or poles or whatever. I mean, this is a genuine holomorphic function, because these are just the multiplicities. And I do the same. This has to be the exponential of some other holomorphic function. And by looking at the growth at infinity, I know that this function is going to be linear. It's going to be exactly this one for some c. And once again, this is an algebraic relation, non-trivial one, satisfied by x of z over c of z, over the rational functions. Okay, but that's not okay. We know this is not the case. So this function g must have a zero in the complex numbers. And then you iterate this and you get infinitely many solutions. Okay, and just to comment, so you were saying about computing these solutions. This approach is not very effective, right? I mean, this is a proof by contradiction. I assume that this is finite in zeros, and then I say, oh, it's transcendental, so it can't be. So written in this way, it doesn't help you find Zn. You can probably work it out, but I don't know how to do it personally. Not from this sketch. Okay, now exercise for the audience is, repeat the same process for any other polynomial into variables. Okay, you have to add some assumptions. I mean, of course, be reducible, because we're talking about irreducible varieties. Why think about multiple components when you can just take the reducible components? And the extra condition that you want is also that the polynomial actually contains both of the variables, and you can check it easily. If it doesn't, then something different happens. Okay, and in general, you're not going to find infinitely many solutions, but these are special cases.
Vincenzo, just to remind you, you're about a bit less than 5 minutes.
Oh yeah, because then we make a break. Yes, no, that's great. Yeah. Okay, no, that's good. Okay, so this is the super easy case, like z equals e to z. How do you justify it as infinitely many solutions? And you can do this with this particular strategy, three steps, and you're done. Okay, so now let's make a slightly more challenging example where we have to do something just a tiny bit more sophisticated, but not by much. Okay, so we actually work in this case in n equals 2. Maybe before reading this entire line with the equations, this is the equation I want to solve. E to z plus e to 1 over z equals to 1. Okay, once again, but now it's too easy to answer because you know where this is going. Is this going to have finitely many or infinitely many solutions? None? Any opinions?
I always go for infinite. It's the safest bet. But
yes, it is. Yeah, so this is another case where we expect to find infinitely many. Well, I mean, we're going to find infinitely many because the situation is actually pretty much the same as before. Okay, so let me just unpack for a second what's going on here with the variety V. So in this case, so you look at this, it looks like an equation in one variable. And now the best way of dealing with this, because this is 1 over z, which is annoying, is to, in this framework, you have to do a translation. You add an extra variable z2, and then you say z1 and z2, the product is equal to 1. That says that z2 is equal to 1 over z1. And then you say that w1, w2, which would be their exponentials, their sum is equal to 1. Okay, so you translate in this way with 2 using n equal 2, and then you look at this intersection of v with the square of the graph of x, and you get, and so we're looking at this kind of points. Okay, solutions to this equation. Can we solve it? Well, let's try to do the same stuff we were doing before. Suppose that this function doesn't vanish for all the points, well, not in C, because now there's 1 over z, in C minus 0. Of course, there's a, the domain now is not all of C. Okay, so I would like to say, oh, well, f is the exponential of some holomorphic function from C star to C. Okay, and I see very diplomatic reactions from the audience. At least the faces I see, I don't see anyone judging me. But of course, you can't do that. C star is not simply connected, so it's a very bad idea to just try and take the logarithm of a function there because it doesn't work. Stupid example, the function z doesn't vanish on C star, but it's not x plus something else. If you try to compute the log of z, you do the integral of z, dz over z, and you have a period around 0. Okay, you can loop around 0, you get 2 pi I, and so you don't get a holomorphic function. You would have to take branch cuts, but that's not what we were trying to do here. But z is the function that saves the day here, because, well, let's see what happens. I mean, let's try to do the logarithm of this function f. So we do the integral of df over f. We loop around 0. So I chose a particular one, particular circle, because then I got a number from Wolfram alpha in my case, because I'm not able to do any computation by myself. I get 2 pi I, so I can just divide f by z. So again, I changed the function. I will use this function g, f over z. And now the integral of this function around 0 is 0. There's no period for this function. Okay, which means under this assumption, under this assumption by contradiction that this function doesn't vanish, it means that I can integrate this and I get a log of g. Okay, so I can write g as the exponential of something else, which means rolling back that f is z times e to phi z for some holomorphic function. And again, now I can use the growth of the function to understand how it looks like. And in this case, it's going to look like this, because now there's 2 points at infinity. Okay, there's the actual point at infinity, but now there's also 0 because I plucked it out of the domain. And that's what I'm going to see. But now I use the fact, I don't just know that e to z is a transcendental function, but I also know that e to z and e to 1 over z are algebraically independent over the rational functions. So this is Ax-Lindemann Weierstrass. Okay, very special case that you can probably do by hand by derivating the algebraic relation a few times. So you can prove it directly. Okay, these are algebraically independent over Cz, which means that this g of z equals to e to z plus c plus 1 over z. It doesn't work. It's a contradiction. This would be an algebraic relation. You can't have that. So this function has to vanish. And once you know how to do that, you just repeat this argument after removing, every time you find the next 0, you find its multiplicity, and then you take it out by dividing by this power. Okay, so this is how you do the easy case. After the break, because now we have a break, right? I'm going to tell you the nice case with projection of dimension bar.
All right, thanks. Let us thank Vincenzo for his great talk. Right.
This is still more, it's very similar to what we were doing, what we were discussing before.
Right.
So if you want, I can jump in and tell you a bit what happens in this.
Sure.
Okay. Okay. I guess how much time should I spend on this? 10 minutes, 15?
I think this time will be, everyone should freely feel to ask questions whenever they have some.
Okay.
Could I just ask something before you start?
Yes.
We know the existential closure or the existence of roots of suitable equations implies the quasi-minimality for the full exp. Does the argument work for subsystems? I mean, say for raising to powers or I mean, I know it's true there for generic powers anyway, but can you do the same argument? Is it the Kirby-Bayes argument for just raising powers? Or say,
I think that's what they prove in that paper, the long one with different types of.
I can't remember.
It's gamma. What's the terminology they use? Gamma fields, gamma. So when you add the graph, you can add the graph of exp, but you can also add other graphs.
Yeah.
But I don't. I don't remember right now whether the raising to powers function is included or not. You're right, because they. At some point, they give up and say, we studied these 3 families, but because they can't give a uniform treatment of all possible situations. But I think raising to powers is included.
Yeah, but it's real powers, right?
Oh, sorry. Oh, no, you're asking general powers. I see. Yes.
Yeah. Well, no, I was asking for real powers, but no one seems to have done anything about complex powers. I mean, or except
yeah,
for
it's
just
mysterious. I mean, the
Anyway,
first obstacle is understanding Boris's proof for the real powers.
yeah.
Which is very, I mean, it's ingenious. Yeah. Now for complex numbers, I don't know. It's a conversation I've had with people a few times, but I have no idea.
Okay. Right, I'll mute myself.
Okay. So yeah, it's okay. So the case that I just want to say, I'll try to make this quick, is that now we take an algebraic variety of dimension at least n, so at least as big as the graph of the exponential function. Projection onto the additive side, so to the c to the n, is of dimension 1. And then you also add this condition that this projection is not contained in a translate of a Q in a subset of c to the n. Okay, remember this kind of Shannon, the consequence of Shannon, this kind of situation here. We see, I mean, it's going to come up. I mean, you see exactly where it comes from. And I mean, we may assume that the dimension of the variety is exactly n. That's more for technical reasons than anything, because then the argument is it works well. And then, of course, it implies the general case. Okay, and we can prove that this set is non-empty in, I would say, almost exactly in the same way. It's just that the domain change. I mean, the objects change, but not the result itself, what you get. So let me now fix some notations. Now you're looking at this projection of the variety V. This is of dimension 1, so it's a curve. Okay, so I'm going to call C, not the curve itself, but some different model of the same function field. So something birational. So I'm going to take a projective non-singular curve, birational with this projection. I take an empty set, non-empty finite subset of this projective curve, such that now C minus S is in bijection with an open Zariski dense subset of this projection here. Okay, so basically it's birational, so it's going to be, so a subset of this one is going to be in bijection with C minus some finite set. So I want set S to contain at least as enough many points to have this bijection. Let small g be the genus of C, and S be the cardinality, small s the cardinality of the set S. Okay, now technical observation. I would say that in this setting, the variety V is essentially defined in this way. Okay, modulo some small stuff, small in the Zariski sense. So the variety is essentially defined by one polynomial. So you say that Z1, Zn are in the curve, and then you say that the rest of the coordinates satisfy a polynomial. What's the point of this? The point of this is that we can forget about all this business, and we can say, oh, to find points here, I just have to solve this equation, pz1 e to z1 zn e to zn equals 0, when z1 zn is varying over the curve C. Okay, that's the point of this technical business, is to have a single polynomial, an actual function I can write down. Okay, and now I want to prove that this one has to vanish somewhere. And so we do the same stuff as before. We think about it in the same way. I take psi, this function here, which is a holomorphic function on C minus S, okay, outside of these finite many points. Okay. Suppose by contradiction it doesn't vanish. Okay, and then I can take this differential form, the logarithmic differential of psi, and look at what it does on C minus S. And now, once again, the situation is like before. I want to integrate this, and if I can do this, then I get the psi is the exponential of something else, some other function on C. That's not always going to be the case, and that's exactly what happened before. We had C minus a point, in the case of V2 EZ, V2 1 minus Z, and that point is a problem. Now you have periods around that point. When you try to integrate this, you get 2 pi I. Okay, so we need to do some work in the same style, and so you let me enumerate these points in the set S, in this finite set S, and I just remind you, that this is classical Riemann surfaces stuff, like Riemann, literally Riemann. There's going to be G linearly independent rational differentials of the first kind on C, so they have no poles anywhere, just holomorphic everywhere. There's going to be another G differential forms of the second kind, and you can put the pole at P naught. I'm just going to do this to make everything well defined for what I need. And then there's going to be a further S-1 rational differentials of the third kind, and I can choose them such that each one has exactly a simple pole at Pi and nowhere else, well, except for P naught, and some pole at P naught. Okay, classical stuff. Now I'm just going to give some names. Rho 1, Rho 2G are the first and second kind. Sigma 1, Sigma S-1 are the third kind differentials. Okay, just to remind, to look back to the previous examples. For example, if you take the curve is P1, it's just a projective space, projective line. Genus is 0. You take, I don't know, 3 points. And then there are basically no first and second kind differentials. Well, not in the sense that there aren't any, but they're all exact. So if I want to work modulo the exact ones, they just disappear. And then for 1 and 2, I can choose these two. Okay. These are going to have simple poles at 1 and 2. Okay. If I take an elliptic curve, then I mean this is just in case just to refresh what this stuff is. These are the two differentials, first and second kind on an elliptic curve. Okay, so you can compute them explicitly. And now, now what do I want to do? Well, the point is that I want to integrate this guy. This guy is going to have periods, but I want to cancel the periods with functions with rational differential forms. So functions that I understand that are not coming from transcendental stuff, not coming from X here. And well, you can do this. And now there's a bit of linear algebra, some bookkeeping, but nothing deep. I think that at this point I should probably try to make a picture, but the point is, and I don't know how good I am at doing this. So your algebraic variety is going to, as a Riemann surface, it's going to look like this. It's going to have G holes, and then you're plucking out S points. And your problem is that you can integrate in a loop around like this, around the point that you've plucked out. And that would be similar to what we've done in C-star. And you can also integrate around this kind of loop. Okay, and actually these kind of loops, there's 2G of them, because you can loop around. For each hole, you can go into two different, so these two are actually equivalent, but there's also this other direction. And here you can say, I mean, I said I wasn't very good at drawing. So this is the situation. You have your differentials, and I can just rescale them. I can do a change of basis such that each of the differential forms that I had, first kind, second kind, and third kind, correspond exactly to this loop. So and by this I mean that when I integrate around this loop, there's going to be one differential form that gives me 2 pi I here, and all the other ones are going to give me 0 when I integrate around this one. Okay. And of course, the ones that have a residue around this extra point are going to be the third kind, the differentials of the third kind. Anyway, I mean, you can just do a change of basis. The nice thing is that I can make everything 2 pi I, just linear algebra, which means that, well, I can integrate these functions, these differential forms. They don't define an holomorphic function on C minus S, but if I take X, they do, because the 2 pi I disappears. So this is well defined. This the exp of the integral is well defined, and these are nice holomorphic functions on C minus S. Okay, now I take the psi of psi. When I integrate around all these loops, okay, the ones around the holes, but also the one around the points in S, I always get multiples of 2 pi I. So I just look at what are these numbers. Okay, and in principle I can compute them. And I just say, okay, so I can just write this one as a sum, as a Z linear combination of the differential forms that I have, plus something which is exact, plus some tau, which is exact now. I mean, this is an exact form because when I integrate around every loop, there's not going to be any period, because the periods that I see here are the same ones that are coming from this combination of differential forms. which means, in other words, I can write psi as a product of the special functions, some powers of the special functions, times something which is a genuine exponential. Okay, and that replaces the first part of the argument as before. It's just done for a general curve instead of just c and c minus a point. Okay, yes, and just, yes, I wrote here a reminder. I mean, we were doing this argument here. The z is just playing the role of one of these differentials of the third kind. Okay, and z is just, I mean, if you unpack this calculation, that's exactly x of the integral of z, the z minus z. So this is the differential form of the third kind in this case, and it's trivial, of course, that if you do x, you get z back. Okay. In general, it's not always going to be of this form. I mean, it could be something else. Okay, so this takes care of this part. And now, once you have this, so you have this nice equation between the logarithmic differential of the psi, the function where we want to prove it as zeros, and this nice equality here. And the nice observation is that now psi is meromorphic on C. I can extend it to a meromorphic function. Okay, this is reproducing the argument where we were saying, oh, phi is equal to z plus c plus 1 over z. That was the special case of the previous equation, but in general, you can do similar argument. So you just look at every point of S, you choose a local parameter in the curve C at S, and then you look at the growth of the function close to that point, and then you see, I mean, you just look at this product here. These are coming from rational differential forms, and this psi is the worst thing that can happen. But you know that this is a polynomial containing some exponentials, so you know what they do, and you see that the bound is, you can bound the growth of these functions, and then you discover, oh wait, this function doesn't have essential singularities at S anymore, and so it's meromorphic. It's meromorphic, it means it's rational. And I would say we're almost done now, because what did we prove is that this logarithmic differential, even though psi is, again, a polynomial containing some exponential functions, this one is rational. Okay, because these guys are just the rational differentials. This tau was the exact form that was left over, but we just said, oh, it's day phi, and phi is meromorphic on C, which is great, because now the people familiar with X know that now there's a problem. I can, so to make this precise, you now make this into derivation. So you divide by, you choose a rational function z, non-constant on your curve, whatever it is, just as long as it's rational and non-constant. You define a derivation on on these functions, and then what we just proved is that this derivative of psi is equal to psi times a rational function. And now you just do the unpacking of the fact that psi is a polynomial containing exponential functions. And that gives you an algebraic dependence between e to z1, e to zn over the rational functions. But then once again, I mean, Ax-Lindemann-Weierstrass says exactly, if this happens, then z1, zn, there's a linear combination over Q of z1, zn, which is constant on the curve, which means this projection is contained into the translate of some Q linear hyperplane into C to the n, and that's a contradiction. So we said the assumption was that this is not the case. And that's it. If you want to do infinity-many solutions, you just keep doing this. You just keep removing, you have this set S, which you're free to grow as much as you want. So you just add you find a new point, you just add it to S, to the set S, and you keep going. And then you find infinitely many points in C that give you points in the intersection between V and the graph of X. Okay, that's it. I can actually stop here. The next slide is just a summary of everything. I guess I'm going to leave this one here.
All right, so thanks again. Thanks again, Vincenzo, for the talk. And now, do we have any questions we'd like to ask Vincenzo?
I honestly forgot what a local parameter means. Sorry.
I mean, a local parameter means it's a function which has a simple zero
Oh, okay.
at that point, and so you can treat it as a coordinate
Right.
at that point. Well, it doesn't have to be zero, but no, well, it is.
So I have a question. Is it the first time that the Axindemann-Weierstrass is used in trying to answer some of those questions?
Possibly. Well, I mean, it depends on how wide is the space of questions you're talking about, I guess. But this specific one, I mean, I remember that David's argument, for example, was not using Ax. To my memory, there was no mention of Ax in that kind of proof with a single polynomial. And you're right that it doesn't intervene even in Boris's proof about this raising to powers business. So he's not using, he's actually using, well, okay. So the correct answer is yes, it intervenes in that case, because Boris says if Chandler's conjecture is true, then there are some constraints on the distribution of points that tell you that there must be intersections between those particular algebraic varieties. But then, and then there's the base Wilkie paper, where they say, well, Ax, well, not Ax Lindemann-Weierstrass, but Ax Schanwell implies a certain inequality, and that inequality is enough to do Boris's proof as long as these linear spaces are generic enough. Yes, but it's not Ax Lindemann-Weierstrass. No, I don't think so. Yeah, so the algebraic independence of these exponentials probably never came up because it's specific to this situation where the Z1, Zn are varying over an algebraic curve.
Right.
Yeah.
Do we have any other questions?
I have a question, and it's just for getting a better understanding. I really don't know beyond the trivial examples, how are the algebraic varieties that may have a finite or empty intersection with gamma. So maybe do you have some examples?
Yeah, that's the funny part. I mean, if I try to give an example, it's going to be trivial for some reason. Because because as I was saying, it's hard to actually say this variety does not intersect the graph of X, because you may encounter problems with the transcendence of the values of X. But usually the problems, the trivial problems come from, for example, when you have a linear dependence in the variables Z1, Z2, and a different multiplicative dependence between the multiplicative variables. And maybe this is what you were saying, what you meant, what you were saying when you were saying, I just know the trivial examples. So if you take this variety V, that's not going to intersect the graph of X because there's an obstruction, there's an easy obstruction, right? I mean, if this one is equal to 1, then this product is supposed to be E, not 2. Yeah, a non-trivial example where this is empty, I'm not able to produce one now.
Anyhow, this example is already quite clarifying to me.
Okay, so do we have any other questions?
I have a quick question. So maybe you mentioned this, Vincenzo, but I missed it. So do you also prove a similar theorem for abelian varieties or, I don't know, elliptic curves?
Thank you. Not yet. and not yet is, yeah, I'm not sure how to answer, because on the one hand, so if you take the Weierstrass P function instead of exp, so you take the elliptic exponential, you can definitely repeat some of, a big chunk of this argument. But then there's a technical thing which I haven't understood yet, whether it's essential or whether it's just a triviality that you can get rid of by rephrasing things. But the P function has poles all over the place. And this is annoying because then when you want to do this logarithmic differential form, you get lots of simple poles everywhere. You get residues at all the lattice points. But for example, the projection of the variety is a curve of genus 1 that's going to contain only finitely many periods, only finitely many integral points. Which means in that case, you can repeat this argument, presumably. But I find it a bit strange now that the curve, whether the curve can contain infinitely many integral points or not, I don't really think it should intervene. So maybe there's a better way of twisting this argument so that it's not. I think that there's just something specific about exp in this argument that you can, translate and do differently when you use P. But not yet.
All right, thanks.
Okay, so last call for questions. If not, let us thank Vincenzo one more time. And thanks everyone for being here. We'll see you all next week.